Circular motion, we start with a real world problem. The car is able to round the curve because of the friction between tire and pavement. So if you look at the curve, the friction always points to the center of the circle. Now from the car to the plane, there is no sideways friction force that the plane can use because there is no solid friction between the air and the plane. So the car is able to turn the corner due to the friction force which act as a centripetal force. What about a plane? There is no friction involved. So using control surface on the tail and the main wing, plane can execute 3 types of maneuver: and pitch, ailerons, and horizontal stabilizer act together. So the roll maneuver that gives the plane a centripetal force, as we will see on the next slide. Let's take a look at the as a plane banks or rolls, the lift vector begins to have a horizontal component. You can see, okay, horizontal component actually act as a centripetal force. You can see the yellow one. So the lift force has 2 components when it's banking, and that the yellow horizontal component acts as a centripetal force. So centripetal force causes a plane to begin traveling in a horizontal circle. That's the gravitational force, and that's the lift force. And the lift force has 2 components: vertical component and the horizontal component. And the yellow horizontal component actually acts as a centripetal force. So centripetal force is always provided by something. In this case, centripetal force comes from the horizontal component of the lift force. What happened to vertical component? Vertical component is cancelled out with the gravitational force. So vertical component upward, weight is downward, these 2 cancel out. But we have a resultant force as a centripetal force. And you can see the plane is moving a circular motion. So take a look at this car. You can see in a diagram, instead of component of the lift force providing a centripetal force, a component of the normal force does so. So you can see that's gravitational force downward. But reaction force has 2 components: vertical component and horizontal component. Vertical component is equals to weight, so they cancel out. But a horizontal component of the reaction force provides centripetal force. So we're going to demonstrate the circular motion here. The first thing is, of course, you need to turn on. So start flying. So yeah. There are 2 forces acting on it. One is gravitational force, one is the tension force. But the tension force has 2 components. One is the vertical component, one is the horizontal component. So we're gonna investigate this first. Instead of bird, I have a flying pig here. Let's say this is the horizontal. Okay, and this is vertical, the horizontal component, guys, right? As you know, the just now the bird is moving circular motion, so the horizontal component provides the centripetal force. So Ft sine theta equals to m omega squared r. And we have omega squared r over g. Very beautiful. right?
If we change it, you know how.
And this is the h, the height. Okay, this is the height, 90 degree. And tan theta equals to what?
R over H.
R over H, please. Okay, that's nice. Okay, so we're gonna plug in tan theta inside. So that is going to be R H equals to omega squared R over G. And we're gonna cross multiply. And we're gonna write it down, our final form. H equals to G over 4 pi squared times T squared. Leon has Leon right now started making his table. Yes, 3 trials. Okay, that's gonna be time, yeah. Small t, you can use small t. T average, yeah. Okay, very good.
Hi, my name is Jun, and this is the visualization of physics experiment on research question, how does the time period of the stopper depend upon the length of the string? So first of all, what am I investigating? In this experiment, I am investigating circular motion. As its name suggests, uniform circular motion refers to a circular motion at a constant speed. However, during uniform circular motion, its direction of displacement and therefore velocity and acceleration change constantly as it rotates in a circular motion. According to Newton's first law of motion, F is equal to ma. The presence of change in a in acceleration indicates that there is a force directed towards the center of a circle, causing the presence of acceleration. So in this experiment, I investigated the effect of the length of a radius of uniform circular motion on its time period, then derived the gravitational force acting on the mass. My independent variable is length of string used in circular motion, measured in meter. My dependent variable is time period, measured in second. My control variables are mass of stopper, mass hanging on the string, centripetal force, including friction and air resistance, and properties of string. This is how I conducted the experiment. I hang 2 different masses, one of mass 200 grams and one of mass 20 grams on both ends of the string with empty pen body between it. As I spin the smaller masses, its centripetal force lifts the heavier mass. Using Newton's third law, I can derive the centripetal force is equal to mass hanging times gravitational force acting on the mass hanging on the string. To effectively measure the time period, I allow 20 complete oscillation as it has relatively small time period, making single oscillation hard to measure.
So this is my setup for the experiment. I have tied a mass of 30 grams and 200 grams to each end of a string with the casing of a pen in the middle. I have used tapes to help me indicate the length of the string, so when I start spinning my object, I can see whether the length of the string would stay constant. I will also be using my phone for the stopwatch. So after initially spinning the object using the pen casing, I will make sure that the object seems to be spinning with a constant speed before starting to measure the time taken for 10 oscillations. I will do this because only measuring one oscillation would be too hard to do as the time would be too short. I will then calculate the period by dividing each of the results I have obtained by 10. The heavier mass would provide tension so that the other object would be able to experience circular motion. By deriving from the formula of centripetal force, we can see that the time period squared is directly proportional to the radius, in this case, the length of the string being spun. From this, we can expect the graph of the period squared over the length to be linear, as shown in the sketch of the graph on the right. Thank you.
By substituting formula for acceleration in circular motion with the process presented on the left, we can derive the final equation of t squared is equal to constant k times the radius of circular motion. As shown on the equation, t squared and r has direct relation, and therefore we can expect the following graph when y-axis is plotted as t squared and x-axis is plotted as L of a string. It is also possible to deduce the gravitational force. We can derive gravitational force G from the equation by replacing it with gradient. G is equal to 4 pi squared m divided by mass hanging on the string. It is also possible to deduce the gravitational force. We can derive gravitational force G from the equation by replacing it with gradient. The gravitational G is equal to 4 pi squared mass of stopper divided by mass hanging on the string times the gradient.
In this experiment, I will be investigating on uniform circular motion. UCM is when an object goes around in a circle at a constant velocity. But since the velocity is a vector quantity, it also moves in the direction of the object. And since velocity keeps on changing, there's the presence of acceleration pointing inwards even though the object is moving at a constant speed around the circle. According to Newton's first law, force equals to mass times acceleration. This means that there is also a force in the same direction as the acceleration, which is towards the center of the curvature, which is called the centripetal force, and it is perpendicular to the direction of the velocity. This force causes the object to move in a uniform circular motion. If there weren't any inward force, the object would have gone in a straight line. In this experiment, I am investigating the effect of changing the radius of the circle in which the object is moving upon the time period and derive the gravitational force acting on the mass. The independent variable will be the length of the string measured in meters. The dependent variable is the time period measured in seconds. The controlled variables are the mass of the ball or stopper, the mass hanging on the string, the method of spinning, friction in the system using the same tube, and properties of the string used in this experiment. I am using 200 grams for the hanging mass, 30 grams for the ball, fishing string, and a hollow pen tube. You will see that the centripetal force will lift the hanging mass. Using Newton's third law, we can calculate the centripetal force as the hanging mass times the gravitational force acting on the hanging mass. Next shows what the experiment looked like. 1, 2, 3, 4, 5. 2. 2.03. 2. 2. 1, 2, 3, 5. 2. We can form an equation using the two equations on the top right of the picture and result in a direct proportional relationship between 2 squared and L, which is the length of the string. Using the same formula in the graph, we can find the gravitational force G by switching it with the gradient in the formula, in this formula right here.